Hi everyone, my name is Holden Hinkle. I'm a launch school student and I recently finished the core curriculum. Thanks for joining me today on my Tech and Talk. The title of it is My Adventures Building Maze Craze. About this talk, I'm going to discuss the backend system of a game I developed over the course of 7 to 8 months while I was working through the launch school core curriculum's Ruby track. I'll discuss various problems I encountered along the way and how I solved them. I'll also demonstrate various aspects of the system and we'll review some of the code together. I'll briefly discuss and demonstrate Ruby's thread, queue, and mutex classes, which are at the core of the background job system I built for the game. And this talk will last approximately 60 minutes. What I hope you get from this talk: at every opportunity, I'll try to tie topics back to Launch School's core curriculum. I hope you walk away from this talk knowing that this game is simply the result of implementing the fundamentals taught in the core curriculum, and that everything I cover is well within reach for you. If I could build something like this, so can you. Some background. I was completing course LS-170 Network Foundations, where Launch School suggested that we take some time to build 1 or 2 small Sinatra applications. At the time, a fellow student named Marcus Unger gave a tech and talk about prototyping a game in 30 hours, which I found very inspiring. This was last March, I think. So when I was considering what kind of application I wanted to build, I knew I wanted to create something that would really challenge me, something more sophisticated than a Twitter clone or a Facebook clone. And I also knew that I just didn't want to take a week or 2 off to do this. I actually decided to give myself a whole month. Actually, this project went way past those 160 hours or 1 month. But also, I knew I wanted to have, I was finishing up the backend track, so I knew I wanted something with a complex backend system. And I kind of guessed that by the time I was finished with the backend system, that might kind of correspond to me finishing the front end of the launch school curriculum. So I knew I wanted something that I could also implement, all of the JavaScript, all of the front end stuff that I was going to learn. So, and I wanted something that I could really, that could really show off everything that I learned at launch school. So at the time, my kids, who were 8 and 11, were playing a couple of different puzzle games on their iPhones and iPads. One was called Fill One Line Puzzle Game, which it's a simple maze game with 1 start and 1 finish. And the goal of the game is to get to this from the start to the finish, filling in all of the gray squares. It's a fun little game. The other one is Flow Free, which is similar. It's got some differences though. One is that it has multiple endpoints. For example, you would connect the red endpoints to each other, or the blue endpoints to each other, so on and so forth. There are also different types of different square types that affect the gameplay a little bit. So I was intrigued by these games, and they actually reminded me of something a number of years ago where I was playing a game on my phone. It was a similar sort of puzzle game, and the thought occurred to me: who comes up with all these boards for these mazes, or whatever it was I was playing? I can't actually remember at the time, but the key memory was, who comes up with these boards? How do they do it? And I thought to myself that it must be the most tedious task in the world, because so many boards must be invalid. Out of all boards that are evaluated, I was certain that only very few boards actually ended up into the game. So anyway, it reminded me of that. And I thought, well, how cool would it be to build a game that automatically created all the boards? That seemed like a very cool task to solve, problem to solve. So as I was entering course LS-180 Database Foundations, I knew I was about to know enough to build the back end of the app. And I knew that by the time I finished the core curriculum, I'd know enough JavaScript to build the front end. So I decided then that I would try to sort of replicate these games and add my own twist to them. So my game is called Maze Craze, as you know, and it's a combination of those two games. So just to go over the gameplay briefly, there are 5 maze types in Maze Craze. There's a simple, bridge, tunnel, loop, and mashup maze type. Mazes can have one start and end point or multiple start and end points. All squares must be used except for the barrier squares, which you can't move to. And all squares can only be used once, except for a type of square called a bridge square, which must be traversed both horizontally and vertically. So I have some screenshots of the game itself. Today, I'll only be demoing the back end. I have a friend who is the great designer. Her name is Tanya. She did these she did this work for me for free. I really appreciate her work. So this is these screenshots. These mock-ups are actually not valid mazes. I didn't send her, I sent her the specs on the different types of maze and square types and things like that, but you'll get an idea of what everything will look like or should look like. This is a representation of a simple maze, and you simply go from a start to a finish, or you connect the dots where you connect the colored dots with each other. So green to green, blue to blue, pink to pink. The next type of maze is a bridge maze, which has a unique square type called a bridge. And that, one moment. I'm just getting an alert here. Okay, sorry, I'm new to this. I'm getting all these alerts from Zoom right now, so I'm gonna try to close those out. Anyway, there's the bridge type, which allows you to both traverse the horizontal access and the vertical access of a maze board. And in order to solve the maze, you must traverse the bridge square both horizontally and vertically. The next one is a tunnel maze type, which allows you to tunnel from one square to another, and you tunnel from each square that is a tunnel square has a corresponding square. They come in pairs. So for example, if you entered, I don't know if you could see my mouse cursor, but if you enter a square with a circle on it, the moment you enter it, you'll automatically exit the tunnel from the, I'm getting more alerts here. You'll automatically exit the tunnel from the corresponding, that has the corresponding shape. So tunnel from circle to circle, tunnel from triangle to triangle, etc. Then there are loop mazes, which allow you to loop from one side of the maze to the other. Again, this isn't a valid mock-up. In this example, the pink, you would loop staying within the same row or column that you're in. Right now, this loop covers 2 rows, but you get the idea. You would exit the left of the maze, come in the right. And then the final type of maze is a mashup maze. This is not a valid mock-up again. A mashup maze is a combination of all the different sort of maze square types. And you can see that the mazes themselves can get bigger. This is a 10 by 10. So there are some other design files. There's the home screen where you choose the type of maze you want to play. So you click on simple, you'll end up on a page that has all of the different levels for the simple mazes. You start at level 1, and then you go to a screen where you see all of the level 1 mazes. So this was built with Sinatra, Postgres, SQL, and Bootstrap. Sinatra is a small rack-based web development framework written in Ruby that has built-in capabilities for routing, view templates, and more. It's very flexible and allows you to set up whatever folder structure you want for your app. I created a modular Sinatra app and implemented the MVC, or Model View Controller architecture, which Ruby on Rails is known for. And Sinatra is introduced in course RB175, Networked Applications. PostgreSQL is a relationship database, and it's introduced in course LS180, Database Foundations. And then I used Bootstrap for the backend, which is an HTML and CSS framework. Sinatra and PostgreSQL are combined in course RB185, database-backed web applications. So the big problem that I first dealt with was how to create the maze boards. And again, that's what interested me so much at the beginning of this project. I wanted to automate the whole process. So the first part of this process is to dissect the problem. So step one, create maze formulas. Each maze has the following properties. It has a maze type, an X value, Y value, number of endpoint squares or start and finish squares, number of barrier squares, number of maze type squares or square pairs. Some of them come in pairs. So if you spec out a maze with the above properties, you arrive at what I call a maze formula. So here's an example of a maze formula, or a couple examples. We'll just look at the first one. The maze type is bridge. It has an X value of 4. X is width, number of squares wide. Y value is 3. That's number of squares high. It has one pair of start-finish squares. It has one maze type square, which is a bridge square, and one barrier square. So all numeric properties, all properties but the maze type, have minimum and maximum values. So as you can imagine, each maze type can have hundreds or thousands of maze formulas depending on the minimum and maximum values for each numeric property. So for example, the X and Y axis could go from 3 squares to 10 squares. So you could have a number of mazes all the way from 3 to 10 squares in width and height. So step 2 is create permutations of these maze formulas. So once the maze formulas are created, each formula is converted to an initial maze board layout represented by an array of maze squares of length X times Y. Permutations of this array are then generated, and the final mazes are derived from these permutations. So what's a permutation? Here's a definition. It's the number of ways to choose a sample of R elements from a set of N distinct objects where order does not matter and replacements are not allowed. When N equals R, this reduces to N factorial, a simple factorial of N. So given the following maze formula, we have an X of 3 and a Y of 2, which gives us 6 squares. So the following maze board layout array is created, and its length is 6. And if we run 6 factorial, we end up with 720 unique permutations, just from that one maze formula alone. So the number of permutations grows as X and Y increases. It grows exponentially. I'm not going to try to read you some of these numbers. They're just way too big, but it happens very quickly. It turns out that computing permutations is one of the most computationally expensive tasks. Someone on Stack Overflow posted that it takes him 25 seconds to run permutations on 10 factorial on a 32-core machine. He wanted to run 20 factorial in less than 2 hours. Someone responded, if it requires 25 seconds to generate 10 factorial permutations, it will require approximately 670 billion times 25 seconds, or approximately 500,000 years to generate 20 factorial permutations. So he suggested that the guy asking the question revise his question. So as you can see, a problem is developing. The game Flow Free has boards up to 10 by 10 squares, which is 100 factorial. How can so many permutations be computed? And there are literally thousands of maze formulas which need to be converted to maze board layout arrays of varying lengths, and each one of them needs to have permutations generated from it. So how is this going to be possible? Well, stay tuned for my solution. So to wrap up step 2, create permutations. The permutations are finally saved to the database unless there's a duplicate and it was already saved, or if you convert the permutation to a maze board and rotate it 90, 100, or 270 degrees, or flip it horizontally or vertically. And if it was already saved, then we skip it as well. So step 3, create mazes. Once the permutations are generated from a maze formula, we iterate through each permutation, convert it to a maze board, and then save it as a maze if the maze is valid according to its maze type and can be solved at least once. So so we've gone over the problem. Now we're going to review the solution for each step along the way. So the first step is to create a settings page for each maze type. And what I did was I created let me move something out of the way. I created a settings table which can be used for any setting within the app. There are columns for integer values, decimal values, and text values. Most of the maze settings are integer values. This table contains all the settings for all the maze types, including Xmin, Xmax, Ymin, Ymax, so on and so forth. So what I then did was created a settings page which has a tab for each maze type, which allows you to fiddle with the settings as you see fit. So looking at this simple maze tab, you can see fields for all the different settings. The bridge maze tab has an additional setting for bridges. Likewise, tunnel and portal also have additional settings for their maze types. So to go back to the PowerPoint here, the second thing that I wanted to do was to create a form that would allow me to manually enter maze formulas into the system. So I did that, which you can see here. It's got a lot of nice form validation to it. And I'll quickly go ahead and create a simple 3x3 maze here with one pair of endpoints and one barrier square. And you could see it was created. Now, if I try to do the same thing again, it will see that it already exists in the database. So that was the second thing that I wanted to do. I thought, wow, that would be really tedious to have to create all these maze formulas one at a time. So I decided to create a page that has a button that says generate simple maze formulas, and each maze type has a similar page with corresponding buttons. So I can simply, and by the way, here is the maze that I just created using the form. It's a 3x3 with one endpoint, one barrier. So I can click this button, and there's an error. I don't know what happened, 1 second. Let me just, I wrote so many comments in my code. Okay, preparing for this, I just wanted to make sure that none of my comments were causing error. Anyway, let me do that again. Of course, that was going to happen. So here we are, simple maze formulas page. We're going to generate simple maze formulas. So you can see you get a notification, the job generate simple maze formulas has been created and queued. If I press it again, it will say that the job already exists, and that's a part of the background job system with the job ID of 409, and the status of it is actually completed. You can see that the system automatically created every possible maze formula for simple mazes according to the settings on the settings page for that maze. So I'm going to go ahead and quickly show you some code, the code that's powering this. So the code that we're going to be looking at is object-oriented code. That's covered in course RB 120, object-oriented programming. And I'm going to quickly give you just sort of an overview of some of the code base very, very quickly. You can see here that I'm in the wrong file here. I cancel that. We're looking at the formulas class, and you could see that there are, here's the main formula class, and then the maze types for each formula. There are classes for each maze type which subclass from formula. And likewise, if we look at the background job system, which we're going to get to, you can see that there's the main class, and then there's a class for each type of job, which subclasses or inherits everything from the background, from the main background job class. So anyway, I'm going to, I've got some notes here that I'm reading. I'm going to go to line 411. And we're going to, sorry, I got the number wrong, 374, which is right here. We're going to review the generate formulas class method. That is called from the background job system, where we run a job called generates formulas. And first we call a method called formula type to class with an argument of a maze type, which is a string, which returns the value to the variable form class. Now, form class is not an instance of the form, sorry, I'm saying form, I meant formula, of the formula class. This variable formula class is not an instance of the formula class, but points to the class itself. So we could call new on it to create new instances of it. But first what we do is we call the class method generate formulas, and we pass in two arguments, the background jobs ID and then this formula class. So we'll go ahead and review that quickly. Here's that method, generate formulas. Now what we're going to do is this classes variable actually is an array of objects that point to various maze classes. Right now in the example that we've been looking at, we've only been working with the simple maze formula type. So this array has a length of 1. There's only the simple maze formula object in it right now. So the first thing we're going to do is call formula dimensions on it. And that's going to return an array of hashes that have X and Y, increasing X and Y's axis, increasing values for X and Y axes. We're going to start from the minimum values, work our way up to the top. And then we're going to iterate on each of those with the each with object method. And we're going to create a new array, which we're going to name formulas, which we're going to save all of these formulas in as we iterate over them. So the first thing we're going to do within this each with object method is we're going to set up a couple of nested loops. Again, this first one, each with object, we're iterating over X and Y, increasing X and Y values. Next, we're going to set up a loop within that. We're going to iterate from the endpoint minimum value up to the endpoint max value. Then we're going to have another nested loop where we iterate from barrier min up to barrier max. And then we're actually going to call generate formulas again. Now, if you recall, the first time we called generate formulas, we called it, the caller was the class itself. This is a class method. But maze class actually represents the simple maze class. So this gets into a topic called polymorphism, which I'll define quickly. And I think polymorphism is very cool. The more you program and the more you become experienced with it, it almost bypasses conditional statements. What it does is let me read you the definition. Polymorphism is the provision of a single interface of entities of different types. In practical terms, polymorphism means that if class B inherits from class A, it doesn't have to inherit everything about class A. It can do some of the things that class A does, but differently. So in this example, if you call the class method generate formulas on the formula class, the parent class, the class method will execute. And likewise, if you call generate formulas on any other formula type class that subclasses from the formula class, like we're doing right now, we're about to call it on the simple formula class. All those classes that have their own generate formula methods that override the formula class will be called. So we're going to call that, and we're going to jump down to the simple formula class, which has the same method. This is going to yield this hash or object back to the block that it was called on. So generate formulas takes a block, and you're going to learn about this as well. And I think actually I can't remember the class that you'll learn that in. It's the one after 101. It's the more advanced Ruby class. But generate formulas takes a block. It yields that hash back, which is assigned to the block formula, the block parameter called formula here, named formula. We're going to assign the background job ID to it, and then we're going to push that formula to this formulas array. The next thing we're going to do is save it. And what we're going to do is iterate through an array of formulas. We're going to convert the formula to a real formula object and then save that to the database. And here we simply create an SQL query to save the formula to the database, and here we execute that query. So that is how we create the maze formulas. Step 2 is creating the maze permutations. And as you know, creating permutations for large maze boards is a near impossible task. So originally I had two thoughts. I thought perhaps I could rent a powerful server on AWS with enough processing power to create these maze boards, even though I wasn't certain I could. I'd have to maybe rent one of the more powerful servers and let it run for a long time. The second thought that I had was to analyze the problem further to see if I could write a more efficient algorithm to generate all the permutations. At the time, I decided to skip this problem and revisit it later because I could complete the app with the small maze boards that I had. A few weeks later, one morning, I woke up in an aha moment and had the solution for the problem in my head. So I realized that a lot of time was being spent calculating permutations on elements of the array that were not unique, specifically the normal squares. And I didn't realize it at the time, but the answer to this problem lies in the definition of permutation, which I gave earlier. And that is the number of ways to choose a sample of R elements from a set of n distinct objects. The keyword here is distinct. So I realized each maze formula could be split into two parts. The first, distinct elements, or the maze squares that are defined by the maze formula plus one normal square. The second part being repeating elements, or the remaining normal squares. So given this maze formula, the following array can be created. The following maze board layout array is created. It has a length of 9 elements. And you could see that there are only 4 distinct elements: the n.1a, n.1b, the normal square, and the barrier square. Then it has 5 repeating elements. So I realized that a lot of time was being spent processing permutations just on these repeating elements alone, which was a useless task. So the number of permutations created by the permutation method of the class array is reduced significantly. So if you look at the original array with a length of 9, if we run 9 factorial on that, we get over 360,000 different permutations. However, if we run a factorial just on the 4 distinct elements, that's 4 factorial, that number is drastically reduced. In fact, by 99.99% to just 24 permutations. So to work this out a little bit further, given, I'm gonna back up here and just let you know that I actually call this initial set of distinct elements a set. And in mathematics, a set is a collection of well-defined and distinct objects. So the initial array of 4 elements from which all permutations are derived, I call a set. So what we're doing right now is we're looking at the result of running these permutations. We're looking at the first one, so 1 of 24. And what we're going to do is add the remaining repeating elements to it. Next, we're going to create 2 loops, one nested in the other. We're going to count down from the index set length, which is 4. We're going to count down to 1, and we're going to call that the left boundary. Next, we're going to count up from the left boundary to x times y minus 1, or 8. And actually, there's a little bit more to it than that. That's a simplification. And we'll call that the right boundary. So what we'll do is we'll continue to iterate these through these, and we'll swap the values of right boundary minus 1 and right boundary. So we'll swap these 2 values. I don't know if you could see my cursor, but on the first line of all 9 elements, we'll swap barrier and normal, which will result in the following array on row 2. And then we'll save that, and then we'll swap the next set of 2 elements with each other, which will result in a new array, and then we'll save that. We'll continue to do that and then loop back around. Now, in doing this, we're creating all the permutations that we need while saving tremendous computational resources. In fact, using this approach, all required permutations are created, and they're created significantly faster when compared to just using array permutation. And again, I'm not going to read some of these numbers because they're just too big, but the improvements are significant. The improvement, the percentage of improvement is the column on the right-hand side. So step 3, actually, so I'm going to just jump back into the code and show you how that works quickly. First, I'm going to go back to the formula class and just show you quickly where the set is derived from. Let me find that again. 545. So here, when we create an instance, of a formula class, an instance variable called set is initialized from the return of calling a method called createSet. And again, this is an example of polymorphism. Every maze type formula class that subclasses from formula has this class. So no matter what method you call, no matter what instance of a formula class you call this method on, you'll get exactly what you need. So there's something unique about this method, which I'll mention quickly. It uses something called recursion, and that simply means that within the body of this method calls itself. So it's sort of a loop. So anyway, this method is where the initial set that I described is created. So now I'm going to jump into the permutations class and show you quickly the code that was represented on that slide. So here, again, this is called via from a method in the background job system. What we do is we instantiate a formula. We make an instance of a formula, and then we call the class method, the permutation class method, generate permutations with the formula object as an argument. First thing we do here is we create an array to store the permutations. Formula.set, again, that instance variable, contains only contains the distinct elements from the maze formula, as I mentioned. We call set permutations here with formula.set, and that returns an array of permutations of that set, and that is right here. And then we iterate through the array of permutations derived from the set. First, we combine that set with the remaining normal squares. And then, just as was outlined in the slide, we create several loops. And in doing so, I'm oversimplifying this, but you're probably happy about that. In doing so, we create a new permutation and then save that to the permutations array. And then we go ahead and we actually save these permutations to the database. So back to the PowerPoint. Step 3 is to create mazes, and I'm not going to review the code here. But once the permutations are generated from a maze formula, we iterate through each permutation, convert it to a maze, and then save it if it's valid according to its maze type and has one solution. So now we're going to get to the background job system, and you'll be able to see more of this in action. So as you can tell, all these operations take time, and I realized very early on in this project that I could either create an app that creates each of these mazes one at a time, or I could have a background job system like Sidekick run in the background and do the same work. So I quickly researched background job solutions, and I thought, wow, writing a background job system would be lots of fun. It looked like a big challenge, and I like big challenges. So I decided to write my own background job system. Now, a few things to note: I had never reviewed any other system's code. I used the PDAC system a number of times, which is a problem-solving system that's introduced very early on in the core curriculum. I believe I can tell you exactly where it's introduced. It's introduced in Ruby 101, again, if you're on the Ruby track. And again, it's covered in more depth in LS 215, computational thinking and problem solving. So again, I didn't review anyone else's code. I actually built a number of features into the background system that didn't necessarily need to be there. As I was building it, more and more ideas popped into my head. And each one of these ideas seemed like a fun problem to solve on their own. So, so this background job system contains some functions, some functionality that doesn't necessarily need to be there to get this game up and going. So first I'm going to demonstrate the background job system, show you it running, and then I'm going to review a few different parts of the code base. I'm going to go over Ruby's thread class, queue class, and mutex class. And talk about some problems that I had, that I discovered some problems that exist in multi-threaded programming, which are fun problems to solve, but also they can be difficult. Like if there are bugs, they can be very difficult to track down. So here is the background job system. Let me jump into that. Here is the dashboard of the background job system. You can see the number of threads. It's multi-threaded. There's a setting where we can change the number of threads. There's one thread with an ID of 268. The status of it is alive and waiting. I can stop the background job system. I can start it again no matter if the system is running or not. If you add a job to the system, that will start the system on its own. Background jobs are categorized into running, queued, or completed. Here is the job that we ran before when we generated the simple maze formulas. That took just 8 seconds. The background job system also has pages where you can look at just queued jobs. There are no queued jobs, or running jobs, or completed jobs. So what I'm going to do here is just start creating the rest of the formulas for the different maze types. And if I look at the dashboard of the system, we can see we're processing job 410 right now, which is, it's generating the maze formulas for the maze tunnel. And when this page loaded, 12 seconds had elapsed. That job has since finished and been put into the completed queue. I can cancel this job. Interesting, there's one thread, but 2 jobs are running. I knew something like this would happen, right? That's just how it goes. Anyway, I could stop it and I can restart it. And there it is. I can increase the number of threads. I'll just, I set 10 as a maximum. It could be more. Here are all of the threads. If a job is running and you change the number of threads, basically it kills the job that's running and requeues it. It also undoes all of the work that had been done already for that job. So basically you're starting over. What I can do is go ahead and create a bunch of permutations for these maze formulas and show you what that looks like. So here's a notification: jobs for the following formulas were created and queued. They are now in this queued section. There's a completed section down here. You'll see them end up there shortly. But if we look at the background job system now, there are 10 threads available. 7 of them are waiting for a new job to hit the queue. Others are being processed right now. We can look at, there are no jobs queued, 2 running. All of these are completed. And then the last thing to show you is that jobs can be, the queue, you can manually sort the queue. So if you had a lot of jobs all queued up to run, and if one seemed more important than the other, you could then stop the system from running. So everything's running right now. There's nothing in the queue. If I reduce the number of threads, my system's really slowing down right now. If I reduce the number of threads, it'll kill all the jobs and restart some of them, leaving some in the queue. I've never seen it so slow before. I wonder if it's partly the Zoom software. But while that's running, I can show you what the database looks like. Here are here's the formulas table where you can it has an ID, primary key. It references a background job ID. It's a foreign key. Type is simple, and then here is the set that was created. From which anyway, we've gone over that. So that's the formulas table. Then we have the permutations table, and you can actually see things in action here. For example, these are, I'm not going to get too into that right now. And then here are the actual mazes themselves, where you can see the final maze board, the number of solutions, the solution, and things like that. So now just to jump back into this, it's still loading. I don't know what's happening. I'm not getting any errors or anything. So I'm going to abandon that for right now. Anyway, the state of the current state, I wanted to go over some of the code with you to show you those various classes that power the background job system. So let's do that. I'm going to close these out. And I'm going to jump into the background worker class. There are 3 classes that power this. There's the background worker, the background thread, and the background job. So the background worker, when it fires up, creates an instance of the class mutex and assigns this to a class, to an instance of the class, an instance variable of the class. I'll get to that later. Mutex is very important when dealing with multi-threaded applications. The next thing that we do when the background job system starts is we create a new instance of the queue class, and that's an instance variable for this class. This is actually a singleton class, and the reason it's a singleton class, meaning there could only be one instance of it, is because of this instance of the queue. The queue, this instance of the queue class, this queue object rather, is able to distribute the objects in the queue as the different threads become available. So it handles that task on its own out of the box. Anyway, when the background job system is fired up, We first enqueue all the jobs. The first thing we do is we run a query on the database and grab all the jobs with the status queue. Then we sort them, and then we enqueue each job, and that means we simply add the job ID into this queue object. Now, a little bit about the queue. I'm going to read some of the documentation and explain more about what's going on. The queue class implements multi-producer, multi-consumer queues. It's especially useful in threaded programming when information must be exchanged safely between multiple threads. The class implements a FIFO type of queue. In a FIFO queue, the first tasks added are the first tasks retrieved. And the queue class comes with a number of instance methods that are similar to array. And these include push, pop, shift, length, size, clear, and empty. And to add items to the queue, like I demonstrated, you simply push them onto the queue or use the shovel operator to get them into the queue. And objects pushed to the queue cannot be accessed with bracket notation and an index value. So this is a big difference between arrays and queues. They cannot be, objects in the queue cannot be accessed with bracket notation or an index value, and they cannot be deleted from the queue. So the next thing to quickly go over is Ruby's thread class. When you instantiate a new thread, the new method actually takes a block. So everything that you want the thread to do has to be defined within the block. So once the thread is instantiated, we're going to want to pull an object off of the queue. In this case, we want to pull a job ID off of the queue. So the method wait for job actually calls pop on job queue, which is a queue object, and pop has an interesting parameter. I'll read you a little bit about that. Another interesting thing about the queue class is that the pop method takes a Boolean argument for a parameter called non-block. If you call pop with an argument of false, pop will block further execution of the calling thread until an object is added to the queue and is popped off. This allows the background job system to always be sort of quote unquote on standby. It's always ready to go when a new job is added to the queue. So within this block, we're waiting for a new job to get popped off the queue or a new object to get popped off the queue. In that case, in our case, it's an integer representing the background job ID. Once we get that, we do a few more things, and we eventually call the method start on the job. It's an instance method. So we'll quickly look at that. And again, it's another example of good old polymorphism in action. Every job type calls the same start instance method. I'm looking for it. But depending on the object that's calling the method, depending on the type of background job, different versions of the run method or finish method or save results methods are called. So as you can see here, generate formulas has its own run and finish method, and likewise, so does generate permutations and generate mazes. So the last thing that I want to show you is, I want to show you the mutex class in action. So right before we called job.start. We call job.update values to start job, which is another job instance method. So what this method does is it creates an array of operations that need to occur to start the job. I'm going to back up here and read you a little bit about the mutex class. Mutex implements a single semaphore that can be used to coordinate access to shared data from multiple concurrent threads. Examples of shared data in the background job system are job queue order and job status. So what I found when I implemented being able to cancel or delete jobs or update their sort order was everything started getting out of sync. Queue orders got so out of whack very quickly. And what was happening, I learned, was that the different threads were accessing different methods that updated job queue orders or job statuses. And if you update one job queue order, all the others can get affected. If you update the status of a job, queue orders can get affected. So what mutex does is it will lock an operation to just one thread at a time. So only one thread could access a block of code. Once that code has executed, it releases the lock and allows the next thread to execute that code, to access the code in the block. And in doing so, it prevents things from getting really out of whack. So there's a method that's sort of in charge of all this called sync updates that can affect a queue order. So I'm just going to review this really quickly because this is really at the heart of the background job system. This is what keeps everything in sync and from falling apart. So the updates parameter in this method is assigned to receives an array, is assigned an array of updates. Each update in the array is a hash. The thread is set to nil by default. This thread parameter is set to nil by default. However, if you're running code that's in the block of a thread, you will send this thread parameter will be assigned. Will point to that actual thread. So if thread, this is truth. The if thread, you're going to call sync updates with the updates here. Mutex, and then we're going to call mutex.synchronize, which is called within the thread new block. Again, if thread, we are in the block of a thread. Else, we're going to create a new thread here, and we're going to call this same method within the block of the thread. So this mutex.synchronize method can only be called within the block of a thread. Only one thread at a time is allowed access to this block, which keeps each job's queue order in sync. So all of the operations that have to do with updating queue order or job status happens within this block. And that's what keeps the whole application in sync. So anyway, that's the overview of the background job system. Now, just to go over the current state of the project, it's about the back end is about 2/3 of the way done. I've not started the front end yet, although I do have the design files. How much time did I spend on this project? I started it last March, and I worked on it off and on up till this past October, and I've easily spent over 300 hours on it. How much launch school do you need to build something like this? Well, you just need the back end half of the core curriculum is required for what I showed you. So um, to complete the front end of the app, of course, you'll need the front end, the front end half of the core curriculum. So the benefits of building this, I gained a lot of experience. I can definitely see a huge improvement in the quality of the code I write from when I started this last March up to this past October. There wasn't anything that I wanted to do that I was not able to figure out how to do on my own. So not only are you learning the fundamentals of computer programming in the core curriculum, but you're also learning to read documentation. You're learning to how to think as a programmer. You're going through hundreds and hundreds of exercises for each course that you're in. All of this adds to your experience and will increase your confidence as you grow as a developer. So, and then the last benefit is that I'll eventually, when I finish this, I'll be able to add it to my portfolio. So that's the end of the talk. I really appreciate you sticking with me, and thank you for checking it out. If you have any questions, please feel free to ask them.
Yeah, Holden, there are 2 questions currently in Q&A section, so you can check them out.
Okay. So Sean, I'm not seeing it.
Okay, I will read it. It's not a problem. So first one is, have you read Buck's book, Mazes for Programmers?
No, I have not. No, suddenly I see some options here in Zoom. No, I have not read that book. I'll definitely check that out. I went into this not wanting to read very much at all. I actually, Marcus Unger's talk last year, he sort of built an app that incorporated mazes or a grid system of some sort. I found that so inspiring. Like, how do you learn how to traverse a maze? How do you go from an array to like a maze with X and Y values? I really wanted to just sort of try to figure out all this on my own. I'm not saying I did it correctly. I did figure it out, but I read very little. Have I done any programming before I joined Launch School? I took a C++ course many years ago in college. I actually took a number of courses through the Tea Leaf Academy, which is what Launch School used to be. A few years ago, Launch School transitioned their really changed the way they were teaching things into a mastery-based learning approach where each course is gated by assessments and so on and so forth. But prior to Launch School being Launch School, they were Tea Leaf Academy. I did a number of their courses. So how did you balance going through the courses and actually doing project work at the same time? I've been fortunate enough that I could do Launch School full time. I have not been working. I started the core curriculum last October, mid-October. It took me just a little over a year to finish. Balancing this was actually not very easy for me. I actually really enjoyed working on this project. It gave me a tremendous amount of satisfaction and sense of accomplishment. And sometimes you don't get that from working through the core curriculum. So that kind of really, sometimes I felt pretty distracted from the core curriculum actually. Um, but I did do it. And actually the reason I stopped working on this in September or October was because I really had to finish the core curriculum. So um, balancing it was not easy. And I think that's partly because of my personality. I generally really like to work on one thing at a time. Um, so I hope that answers your question. Any other questions? Did you struggle with the core curriculum at first? Was there a point where everything just clicked, which led you up to being able to create this maze program? Um, I didn't really struggle with the core curriculum. I guess the answer is no, but I put a tremendous amount of work into it. I mean, every time it came time for me to take an assessment, I would postpone it and postpone it and postpone it. I actually experienced anxiety about taking tests for the first time in my life. In college, I did quite well, never experienced any anxiety. Um, Going through launch school, I really wanted to get into capstone. That was my main goal. And I didn't want to take any chances on doing poorly on an assessment. So I really overstudied. I really love programming. I really love problem solving. In some way, it seems like my brain is kind of built for it, if that makes any sense at a time. I mean, if that makes any sense at all. So um, my answer is no, I didn't really struggle with the core curriculum. Is the code available? Yeah, it's on my GitHub repo. Uh, I could get you that link somehow. And again, some of the code I'm proud of. Some of the code is older, and I definitely want to refactor it, but I'm happy to share it. Here's the link. Let me see here. Does anyone else have any other questions? Do you have ideas for the capstone project? If so, are those ideas related to what you did with this project? Um, I No, I don't have any ideas for the capstone project. Actually, there are a few projects that I have in mind that I want to work on myself. I don't know if they're sort of capstone worthy projects. Um, so the person who's asking me this is also in capstone. We're both in capstone in the upcoming cohort, which starts this Monday. So um, I wouldn't want to do anything like this for my capstone project. Anybody else? Well, I guess that's it. Thanks a million, you guys, for tuning in and staying with me. I've never done anything like this before, and I'm glad to see that there are a few people here who made it through to the very end. I really appreciate you taking the time.